Hi everyone. We're going to look at definite integrals that require u substitution. So we're taking u substitution with indefinite integrals one step further. And what I'd like you to try to do is evaluate this integral that I've written in the do now. Notice that this function here is above the x-axis, so this definite integral represents the true area under the curve. So take a minute, copy that, and see how you would do it. Okay, let's go over how to do this problem. Well, ignoring the limits of integration and looking at the integral of the square root of x minus 1, this is the composition of two functions, and we did say that with u substitution, we let u equal the innermost function. So we let u equal x minus 1. We differentiate it. Du dx here is just 1, and we bring the du by itself, the dx on the other side, and du equals dx. So this integral would become the integral of u to the 1/2 du, which would anti-differentiate into u to the 3/2 times 2/3 plus c. But of course, we're going to convert this back into x. So this is 2/3 x minus 1 to the 3/2 from 1 to 2. And now we can use the first fundamental theorem of calculus. So we substitute the upper limit first. So it's 2/3 2 minus 1 to the 3/2 minus 2/3 1 minus 1 to the 3/2, or equivalently, we could have factored out the 2/3 and worked on just the what's in parentheses, 2 minus 1 to the 3/2 minus 2, I'm sorry, I meant to not write the 2/3 there, minus 1 minus 1 to the 3/2. But in that case, we get 2/3 times 1 to the 3/2. This is just a 0 times 1 to the 3/2. And of course, the square root of 1 cubed is 1. So the answer is 2/3. So this is one way to handle a definite integral with u substitution. Ignore the limits of integration, differentiate it integrate it in terms of u, substitute u back in terms of x, and then use the first fundamental theorem of calculus. But there's another way to do this, which I'd like to go over with you. Okay, so I'm going to rewrite the problem. And I start the same way. I let u equal x minus 1. Du is still dx. But now what we're going to do is we're going to change these limits of integration, which are x limits of integration. These are x limits of integration. So that's why we substituted the 1 and 2, because they're x limits. And we're going to change them into u limits of integration. The way to do that is we take x equals 1, substitute it back here. So u is 1 minus 1, which is 0. So instead of x is 1, we're going to put u as 0. So I'm going to start replacing that. And when x is 2, u is 2 minus 1, which is 1. So I put a 1 up here. This becomes u to the 1/2 du again. The antiderivative is still 2/3 u to the 3/2. But now my limits of integration are u limits of integration. So we do not convert back into x in terms of x. We substitute these limits of integration. So when we do that, we get 2/3 of 1 to the 3/2 minus 0 to the 3/2, which again gives us 2/3. So these are the two ways we could handle substitution with definite integrals. Some teachers insist that we always convert back into x. I like converting into u, everything in terms of u, so we don't substitute back in terms of x. Whichever way we do it, sooner or later, we do get the same answer as you see. So let's just summarize our techniques, and we'll take a look at more problems. So the summary is the following. 1. Use u substitution and translate back in terms of x. Use the first fundamental theorem of calculus in terms of x. So limits of integration are x limits. Okay, now the second way is to, again, now we'll go to the next page. Use u substitution and translate the x limits of integration into u limits of integration and do not translate back in terms of x. Use the first fundamental theorem of calculus in terms of u. Okay. All right, now I just made a few little writing errors here. I put too many i's here. And I think I did the same somewhere else, but I can't find it. Oh, here. Okay, so that takes care of that. Okay. All right. Now, let's see what this means using the calculator. I mean, what are we really doing here algebraically?
To show you the graphical interpretation of u substitution with definite integrals. So I'm going to my home screen here. And I'm going to pick this icon, the parabola to graph. Okay. And I'm going to enter the first function, which is the square root. So I have square root control square of x minus 1. Okay, so we'll graph that. That's our window there. Okay. We could see that graph pretty well. And what we're going to do is, let's move this a little over. If I could do this. Okay. And going to get the area of this curve from 1 to 2. So we go to menu. And we go to analyze graph. And we go to integral. Okay. And I'm going to type in the bounds, even though we can drag this vertical line. I find it more efficient to put in the bounds. So our bounds were from 1. I'll press 1. Enter. Now the upper bound 2. Enter. And my answer here, I don't know if I could grab this, I'll try, is 0.667, which looks like it's 2/3. About 2/3. And I think that's the answer we obtained analytically. All right, now if I graph another function, so I'll go to my tab, and I type in the simpler function that we found through U substitution. And that was the square root of u, but I'll enter the square root of x. Use just a variable. I could use any variable for it. I'm going to control square root x. Right. Graph it, which is in red. And now with U substitution, we claim that the area under this curve. Now, what were the limits of integration here? 0 to 1. Should be 2/3 as well. So let's see. So we'll do menu, analyze graph, integral, and type in. Oh, now it's asking for which graph, because we have more than one graph here. So I'll just highlight graph 2. Lower bound 0. Press upper bound 1. Press enter. And that gives us an area. I don't know if I could grab this over here. Try. Oh no. Very hard to grab it. Wait, hold on. Here we go. And notice that the area under this square root function, the red one, is the same as the area under our original square root function. This involves a little bit of transformational geometry. And when we change the limits of integration, we're also changing the function. So if we translate the square root of x 1 unit to the right, we subtract 1 within the function, and the same is true within the limits of integration. So this is transformational geometry, and this is what we do. That's what we do. But analytically, we do it the way we've discussed in class. Okay. That takes care of the graphical part.
Now let's take a look at a few more problems to practice. So I'm going to add another page. And I'd like you to do these by yourself. Okay, so number 1. The integral of 0 to pi over 4 of sine 2x dx. Okay, the next one is the integral from 0 to 1 of 3x plus 1 to the negative 2 dx. The next one is the integral from 0 to pi over 2 of e to the sine x cos x dx. And the last one is the integral from e to e cubed of 1 over y ln of y cubed dy. Okay, so let's try to convert everything in terms of u. Copy these down and give it a try. Pause the button and we'll go over them. Okay, let's start with number 1. So here we have a composition of two functions. 2x is the innermost function. So we set that equal to our u. du is equal to 2, and we add on the dx. So 1/2 du is dx. That's one substitution we're going to make. And when x is 0, u is 2 times 0, which is 0. When x is pi over 4, u is 2 times pi over 4, which is pi over 2. So this as a u integral becomes 0 to pi over 2 of sine u times 1/2 du. Notice that we substitute this for the dx and these for the limits of integration. So now we just find the antiderivative, and the antiderivative of sine u is negative cosine u from 0 to pi over 2. We substitute the pi over 2. I'm going to factor out the negative a half. We always substitute the upper first and then the lower. So it's cosine pi over 2 minus cosine 0. That's negative 1/2 of, now cosine pi over 2 is 0, cosine 0 is 1, and that gives us 1/2 as our answer. I believe that is correct. And again, when the answer to an integral is a co-function, we put a negative. Okay, let's try the second one. The innermost function here is 3x plus 1. So du is, the derivative of 3x plus 1 is 3. I'll put the dx here. So 1/3 du is dx. When x is 0, u becomes 3 times 0 plus 1, which is 1. And when x is 1, u becomes 3 times 1 plus 1, which is 4. So this is a u integral, becomes the integral from 1 to 4 of u to the negative 2 times 1/3 du. Notice again, we substitute the dx and we substitute the limits of integration there. And we get 1/3 u to the negative 1 over negative 1 by the power rule. So I could take out a negative 1/3 and use the first fundamental theorem on the u part. So this is 4 to the negative 1 minus 1 to the negative 1. So that's negative 1/3 times 1/4 minus 1, which is negative 1/3 times negative 3/4, I think. Hopefully that becomes 1/4. And that's the answer there. Okay, here's another u substitution. The u is the exponent. So u, sorry about that. U is sine x. Du equals cos x dx. And then when x is 0, u is sine 0, which is just 0. And when x is pi over 2, u is sine pi over 2, which gives me 1. Okay, again, we substitute these here. So this, as a u integral, becomes the integral from 0 to 1 of e to the u du. Very easy to integrate, e to the u from 0 to 1, which gives us e to the first minus e to the 0, which is e to the e minus 1, which would be our answer there. And then finally, the last one, hold on, I lost you. Okay, the inner function is ln of y. So du equals 1 over y dy. And that's exactly what we have over here. And then when y is e, u is ln of e, which is 1. When y is e cubed, u equals ln of e cubed, which is 3. So this, as a u integral, becomes the integral from 1 to 3 of u cubed, which is this piece. Okay, I'm going to underline that. This is u cubed. And the 1 over y dy is du. So we put the du there. And I'll underline it in blue so you know. So using the power rule, we get u to the 4th over 4 from 1 to 3. Take out the 1/4 and use the first fundamental theorem on the u part. So it's the upper one first. It's 3 to the 4th minus 1 to the 4th. So that gives us 1/4 of 81 minus 1. And that, I believe, is 80, and that gives us an answer of 20. So that one came out to be a nice answer. Okay, I wanted to go over an AP question that incorporated this. It goes back to 1988. Let's look at the next. Page. Okay, and that is, we have a region R in the first quadrant under the graph of y equals x over x squared plus 2 in the interval from 0 to root 6. Part A says, find the area of R. Now notice, back then we didn't have calculators, graphing calculators, but they did say this is in the first quadrant, this graph, which means that whatever the area is underneath it in this interval, the definite integral would represent the true area from 0 to root 6. So the students was expected to integrate from 0 to root 6 of this function x over x squared plus 2 dx. And you know, one of the techniques in integration is that if we integrate a fraction, and the derivative of the denominator gives you part of the numerator, set u to the denominator. So if we set u to x squared plus 2, the du, well, the derivative of x squared plus 2 is 2x, and then I'll tack on the dx. So x dx is a half du. And then when x is 0, u becomes 0 squared plus 2, which is just 2. And when x is root 6, u becomes root 6 squared plus 2, which gives us 8. So this as a u integral becomes the integral from 2 to 8, x dx. Okay, be careful now. X dx is a half du. That goes up here, because that's the x dx. Notice x dx is here, so that goes here. And then all divided by u. So we take the half. The antiderivative is ln of the absolute value of u from 2 to 8. So we have 1/2 ln of 8 minus ln of 2. And because we'll need it in the next part, I'm going to rewrite this as 1/2 of ln of 8 divided by 2 using the one of those log properties that the difference of two logs is the log of a quotient. That gives me 1/2 ln of 4. And the scalar can be written as an exponent like that, 4 to the 1/2, which is just ln of 2. Okay, now students weren't expected to go that far, but it's going to help us in part B. So let's look at part B. In part B, it says, if x equals k divides region R into two regions of equal area, what is the value of k? All right, now this was a very different question. So to approach it, we know that the integral from 0 to k of the same function would be 1/2 of the answer above, which is ln of 2 divided by 2. And notice I could also say the integral from k to root 6 of this function is ln of 2 over 2. But it's always nice to have a limit of integration of 0. You know, hopefully things will cancel. So let's solve the first equation. Okay, we've done most of the work above. Our u, okay, so going back, our u is still x squared plus 2. Our x dx is still a half du. So I could start substituting that. Oops. So this is 1/2 du over u. When x is 0, u is still 2. And when x is k, u would become k squared plus 2. So that's a very strange limit of integration, but let's squeeze it up there. Okay, actually, I'm going to erase this, and I'm going to try to write that a little better for you so it's not all cluttered. Okay, so let's do that. So I have the integral from 0 to k squared plus 2 of 1/2 du over u. And that's equal to ln of 2 over 2. Okay, so that's still 1/2 ln of absolute u from 0 to k squared plus 2 is equal to ln of 2 over 2. And that's 1/2 ln of k squared plus 2 minus ln, oh, excuse me, this is not a 0, it should be a 2. Oh, another mistake. Yeah, when x is 0, u is 2. Yeah, because I got an ln of 0 and I knew that was wrong. So it's ln of 2 is equal to ln of 2 over 2. Well, this is already positive, and this is positive, because k squared is positive, and add 2, it's positive. So I could just rewrite this as 1/2 ln of k squared plus 2 over 2 for the same reason. I could divide through the 2's, and I get, going to the next page, oh, excuse me, I did make a mistake. I went to the last. ln of k squared plus 2 is equal to ln of 2. Okay, I think that's correct. I hope that's correct. Hold on, let me just look at that again. It's it's ln of, let me just erase this. It's ln of k squared plus 2 over 2 is equal to ln of 2. Okay, I could rewrite this as ln of k squared plus 2 minus ln of 2 equals ln of 2. Add ln of 2 on each side. We get ln of k squared plus 2 is equal to 2 ln 2. So we have ln of k squared plus 2 is equal to ln of 2 squared. Ln of k squared plus 2 equals ln of 4. And now, because logs are one-to-one functions, we could say k squared plus 2 equals 4. And if we subtract 2, we get k is positive or negative the square root of 2. But since k has to be in this interval, we accept k to equal the square root of 2. And that would solve part B. Now part C says, find the average value of this function on that interval. So the average value would be 1 over the square root of 6 minus 0 of the definite integral from 0 to root 6 of x dx over x squared plus 2. We already did this in part A, and we found that the answer in part A was just ln of 2. So the answer is 1 over root 6 times ln of 2. So I wanted to share this AP problem because it was the only one I could find right now that incorporates what we've been doing. Okay, I hope you found this helpful. I wish you a very safe and healthy weekend. Bye.